h minus f of x all over h as h drops to 0 is a formula to find the derivative to us of I state instantaneous rate.
F of x plus h minus f of x all over h as h drops to 0 is the formula to find the derivative to find the slope at one point.
Alright, boys and girls, welcome back to another video. This one is going to be a little bit of an introduction to Chapter 3, some of the boring stuff that'd be nice to get through at home and not have to waste time in class talking about. So the first thing I'd like you to do is in your notebooks, definitely title this 3.1 Derivatives of Polynomials and Exponential Functions. But also take one last time, and I promise is the last time I'm going to ask you to do it. If you can find the derivative of f of x equals x squared using the old school limit as h goes to 0 of f of x plus h minus f of x over h. Find that derivative. Pause the video for a second, do that, get it in your notes, and then hit play when you're done, and we'll talk about what's happening. Alright, hopefully you didn't cheat there. Hopefully you actually did do it. Here it is done out though for, again, hopefully the last time. Again, I'm defaulting to x plus h, not a plus h. I really want my function to come out in terms of x. I want f prime of x, not really f prime of a anymore. So that's why the x plus h is in there and the f of x is in there. And you can see that, just like all of the other derivatives we've been taking, x squareds cancel out in this particular step, leaving you with just the 2xh plus h squared. We go ahead and divide out the h's. We're left with 2x plus h as h goes to infinity. And therefore, we get our f prime of x function, the function that defines the slopes of the tangent lines to f of x, where f of x is x squared. Looks like it's always 2x. So we're going to try to make things easier for you from here on out. We're going to talk about some derivatives of polynomials, and we'll get to exponential functions in class. They're a little bit more difficult to talk about, so I'll save those. But we're going to talk about derivatives of polynomials. So here we go. On to the next slide. Alright, so using some of the background knowledge that you already have, the first thing I want to look at is the derivative of a constant function. So what I've given you over here is a graph that has a horizontal line. That is what the equation of a constant function looks like when it's graphed. So we're talking about things that look like f of x equals c. And it could be anywhere. I just chose a positive c value, I don't know, because I'm a positive type of guy, I guess. And really I want to write this in a different way though. I really want you to consider f of x equaling c times x to the 0 power. So really what a constant function is it's a function where the variable x is raised to the 0 power, making it a degree 0 function, and you'll see the importance of that down the line. All I really need you to understand at this point is that the slope of the tangent line to a horizontal line is itself horizontal, which means that the derivative, f prime of x, is just going to equal 0 for any constant function. So when we have d dx of a constant function, so we'll just say of any constant c, we know that that will always equal 0. So if you see any numeric value, for example, the derivative of -3 is 0, because the slope of the tangent line to f of x equals -3 is just a horizontal line itself, which means that its derivative will also be 0. Alright, so first basic rule out of the way, derivative of a constant, always 0. Alright, next piece, derivative of the identity function. When we talk about the identity function in math, we're talking about the function f of x equals x, that horizontal line that goes from quadrant 3 to quadrant 1, and we know that the slope of that line is always 1. So again, in terms of derivatives, where derivative is just a funky way of saying slope, if f of x is equal to x, it should not be any stretch of the imagination for you to know that the derivative of x is always equal to 1. So the derivative of the identity is always equal to 1. We say that then d dx of x is equal to 1. That's the derivative of the identity. You might be saying to yourself, hey Tamao, you know what? What happens if it's not f of x equals x? What if it's like f of x equals cx? So what if I give you the graph of, a function that, again, goes to the origin. I know my graph doesn't exactly go through the origin there, but give me a break. What about its derivative? And I would say this, go back to your understanding of the limit laws. If f of x is equal to cx, and c is just a constant multiplier, remember how limits operate. This is really, f prime of x is what we're trying to find, is really a limit. And with limits, you can pull constants out in front. So it's really the limit as h goes to 0 of f of x plus h minus f of x, over h. And we know from the previous slide that this piece right here, this limit, the limit of the identity, is just going to be 1, which means that then f prime of x should just equal whatever the constant value is. And that makes sense, because again, think about this particular function over here. What is its slope? Its slope is c if its function is cx. Therefore, what's the slope of the tangent line going to be? It's just going to be the slope of the line itself, which is c. So we say that d dx, the derivative with respect to x of anything of the form cx, is really just the same as saying c times the derivative of the identity function, which is c times 1, or c. So the derivative of cx is just c. I hope you guys are taking the time to pause the videos, get the notes in your notes, rewind if you need to rewind, listen to my annoying voice over and over and over again until you get the basics down. Take a potty break if you need to, because we're about to go on to polynomial derivatives. Press pause. I'll be here when you get back. For those of you that are hanging around, let's talk about that function that we started out with. F of x equals x squared. This, by definition, is a polynomial function. Anything that's linked by addition and subtraction gives us a polynomial. We really do consider this, though, a power function, but for the time being, since we already have dealt with this function many times before, I'm going to come back to it here and just say it's polynomial. And if you remember back to some of our previous notes, we've actually found this derivative, and we found that the derivative of x squared is actually just plain old 2x. And, we've done a bunch of examples. Hopefully you've been doing all of your homework and you've come across this, and I've even brought it up to you. I've talked about this idea that the derivative is a degree less than the function itself. So when you look at, x squared to 2x, you're talking about a second degree or quadratic becoming linear, which is first degree. That would probably lead you to believe that if you took f of x equals x cubed, a third degree polynomial, you should get a second degree polynomial back as the derivative. And in fact, f prime of x, the derivative, and if you want to convince yourself of it, please, by all means, go ahead and do a little bit of limit as h goes to 0. I'm pretty much done with that, so we're going to go here with a little bit of a pattern, that x squared became 2x, that x cubed becomes 3x squared. And if we go one step further, if f of x is x to the 4th, make sure you're sitting for this one. This might just blow you out of your sneakers if you're standing up. The derivative of x to the 4th is 4x to the 3rd. And you might be saying to yourself, DeMeo, I see a pattern, and I really do hope you see a pattern. For anything of the form f of x equaling x to the n, we know about the relationship between the power and the derivative itself. So the derivative of anything of the form x to the n, if you notice in each case, up here, the 2, the 3, and the 4, all became the coefficient of the term in the derivative. So we say that the derivative of x to the n is n, and we're still in terms of x, so we're going to have an x. And then the next thing you want to look at is what happens to the power. Well, this 2 becomes a 1 that we don't typically write, but it really did become a 1. This 3 became a 2, this 4 became a 3. There was a decrease in power from the function to the first derivative, so we say that the derivative is nx to the n minus 1. And I'm going to put that in parentheses so you don't think it's x to the n minus 1. But this is our next kind of big piece. This is really what's going to make taking derivatives easy. This idea that the power of the function drops down in front and we decrease it by 1. We actually give this a name. This is called the power rule. Power rule. Yeah, I'm excited about it. Sorry if I scared you there with that loud music. It's one of my favorite songs, a little snap, I got the power. It works just about everywhere in math. You know, just like limits, we have our basic derivative rules, things that, you know, we're not going to really go through proving. We're actually going to do a pretty extensive look at the power rule on Friday, but some of these other ones, just like their limit cousins, the derivative works the same way. And again, the reason why is the derivative is basically a funky limit. So some of these are just going to be commonsensical to you, but we'll take a look at them and then even, you know, take a look at an example of each. And the first one relates back to what we were talking about before. What happens if you take the derivative of a constant times a function? And just like the constant times a limit and the constant can come out in front, we say that this is equal to the constant times the derivative with respect to x of f of x. And that just allows us to not have to worry about constants, just worry about taking the derivatives of the actual functional part and multiply at the end, essentially. So, you know, going down here to our example, what I would say is, you know, let's look at this as 3 times the derivative of x squared. And we know that the derivative of x squared by the power rule is going to just be 2x. So this is 3 times 2x, which is 6x. Could you have kept the 3 in there and said that 2 times 3 is 6 times x? Yeah, you could, but there are going to be times where pulling the constant out in front throughout the year is a valuable piece, so knowing this basic rule will be very helpful down the line. So, you know, remember, we're dealing with very basic functions at the beginning of the chapter. As we get into some exponential functions, some trig functions, some inverse trig functions, you'll be thankful knowing that you can pull c's out in front. The last thing that we're going to look at in this video is the derivative of the sum or difference of two functions. And I have to be very clear in stating this, that the derivative of the sum or difference can only be taken if both f and g are differentiable functions. So, you know, the assumption here is that f and g are differentiable. Yeah, it says differentiable. I'm not writing the whole thing out, too bad. And I'm sure that you would guess that if you're taking the sum or difference of the two functions and then taking their derivative, it's the same as taking the derivative of the sum or difference. So the derivative of f of x plus or minus the derivative of g of x. And again, what this does is it allows us to break larger polynomials up into smaller pieces. So in this example down here, we're taking the derivative of a 4-term polynomial. What I'm saying is you can take the derivative of each individual piece, so x to the 4th. I'm going to apply my constant rule here, so 2 times the derivative of x squared. I should probably put these in brackets so that they're isolated. Minus 9 times the derivative of the identity, plus the derivative of the constant function 3. And then evaluate each derivative independently. So apply the power rule for x cubed plus 2 times the derivative of x squared. Well, we know that x squared's derivative is 2x, so 2 times 2x is 4x. Minus 9 times the derivative of the identity, but the derivative of the identity is just 1. Plus the derivative of 3. Well, the derivative of 3 is going to be 0 because 3 is a constant. So my simplified version would be 4x cubed plus 4x minus 9. That's my f prime of x value. So very simply stated, you know, taking the derivative of a polynomial, you just take the derivative of each individual piece and then sum or subtract them depending on the operation. All right, so those are some of the basics. We'll talk about exponential functions in class on Friday, and we'll also talk about where the power rule truly comes from, because you guys have enough algebraic background to look at that. All right, see you on Friday. Peace out, Cub Scouts.